I had one of my teachers in high school who was very active. He kept up on a lot of stuff that was going on in discrete mathematics. That's where I learned. That was where I was first introduced to graph theory and how it works. And I just wrote at a time. I actually started learning about it in my
I think both of them.
I didn't understand a lot of it, but
have the same
yeah, we know. I was lucky enough to have that. And then there were a couple other teachers in my school that were AP professors or AP teachers.
Yeah, my last name is.
They kept up on a lot of stuff going on.
My determinant is here.
That and the fact that they were willing to talk to me.
That's why you're doing it, I see. You want to do deal with people out there.
I think the thing that made it was when I got to school, and I was at the point that I didn't even know if I wanted to keep going to school anymore. I was done going into freshman year of high school, and I think most of that was caused by the fact that I knew I wanted to do math, and my eighth grade I took out for one early, and my teacher failed me. Like my grades progressively got worse, and then I went to high school and I slept like the first 2 months of the class, and I had the highest grade in the class, just because of the fact that like homework was really easy for me to do and the tests were really easy. Once you notice that, they started integrating me a little bit more, trying to make me more of a
So our final talk of the morning is Ivan Alsarev from here, from Wyoming. He's speaking on permanent time.
Thank you all, and thanks to the organizers. I want to talk about the permanent rank of the matrices. So, at the end of this talk, I have to convince you that permanent and permanent ranks are important things to look at. So that's my main goal, and my next goal is that I speak slowly. This is my first talk in a conference like Andrew, and so I'm a little stressed. But anyways, so this is the outline, the things that I'm going to talk about. First, I define the permanent using some examples, and then I define the permanent rank of the matrix. Talk about the Young-Use conjecture, who is believed to introduce the permanent rank of matrices, and then AJT conjecture, which is the motivation of this, the Young-Use conjecture, and also the conjecture which relates permanent rank and term rank of matrices, which is the thing that I'm working on right now with trigon shaders. So, but these are just matrices. This conference is about graphs, so I'm going to start with the graph example. So suppose that we have a bipartite graph, and we want to know that how many perfect matchings does this graph have. So, well, I think there are different algorithms to count the number of the perfect matchings. But one easiest thing for me is to look at the bi-adjacency matrix of the graph. Then for every perfect matching of a graph, I can find a diagonal of all points, for example, this main diagonal of the matrix, that corresponds to exactly one perfect matching here in the graph, which is all these horizontal edges here. So the purpose is that, well, we want to relate the number of the perfect matchings of this graph to the diagonals of that matrix. Well, by counting, we can say that the number of the perfect matchings for this bipartite graph is 95. By the way, that PER doesn't stand for number of the perfect matchings, that stands for the determinant of the matrix, which I'm going to define in a second. So let's say we have a general matrix, A, I, J, and N by N matrix, and the determinant of this matrix is defined to be the sum of all the diagonal products of A. So that means that we are looking at all the diagonals of the matrix, all the entries, we multiply all of those entries, and then add them up. That gives us the determinant of this matrix, which has a definition like this. Probably you'll notice that this is very similar to the definition of the determinant of the matrix without those negative ones. So that's the definition of the determinant of a matrix. The thing is that unlike the determinant of a matrix, it doesn't have any kind of easy geometric interpretation, like the volume of a parallel pipeline. But on the other way, it has a lot of combinatorial interpretations, like number of perfect matchings of this of a bipartite graph, or if you have a directed graph and you want to count the number of the directed cycle covers of the directed graph, that is also can be represented by the permanent of a matrix. But what if the matrix doesn't have a perfect matching? Well, this is the first graph that we started, and now I want to delete some of the edges of this graph. Let's say we are going to delete those red edges. So instead of those ones, the red ones in the matrix will have zeros. So this is the matrix, this is the graph without those edges, and then we have this matrix which has zeros instead of ones, some ones here. And if you use Hall's theorem, you can see that in the, for example, first 5 lines of this matrix, there are not 5 ones in different columns. That by Hall's theorem, we can say that, well, this matrix doesn't have perfect matching. Then the question will be, what is the number of the greatest matching in this graph? How many disjoint edges, vertex disjoint edges can we find in this matrix? So for this one, perfect matchings are 0. Number of the perfect matchings is 0. So permanent of that matrix is also 0. And if I look at a 9 by 9 submatrix, deleting the column 2 and row 5 of that matrix, then I can find the matching which has 9 edges in it. So that means that the permanent of that 9 by 9 submatrix is non-zero. And for this case, it is just equal to 18. That gives us the idea of defining the permanent rank of a matrix. We want to know that what is the size of the greatest matching in a bipartite graph. So here's the definition. The definition of the permanent rank of a matrix says that we have a matrix, and by a matrix we find the greatest submatrix, n by n submatrix, which has permanent non-zero, and then that gives us the size of that matrix gives us the rank of the matrix, the permanent rank of the matrix. Well, this has been introduced by Young in his PhD conjecture in 1999, I guess, and he proved some interesting results for the permanent rank of matrices. First of all, permanent rank of matrix is at least half of the rank of that matrix. So he is connecting a combinatorial aspect of the matrix to its geometric aspect. And also for an invertible matrix over a characteristic tree field, we can say that the permanent rank of a matrix is equal to the permanent rank of its inverse. This is in particular important when we'll study the weak tree flow conjecture, which I guess it's been proved, at least we claim that it's proved recently. So this is going to be interesting thing to look at when you're working on that conjecture over characteristic tree field. And also, one more interesting result is that if you have two non-zero, nowhere zero matrices, two full matrices with no zero entries, A and B, and we join those two matrices together as an n by 2n matrix, then over a characteristic zero field, the permanent rank of that new matrix is equal to n. That means that it is a full pair rank. Well, in the original proof, it's not. The matrices don't have to be full. They have to have enough non-zero entries. Well, these are the used results, and then he proposes this conjecture, which says that if we have two invertible matrices, in the previous case, these two matrices A and B are full matrices, but here we have two invertible matrices, and we adjoin A with itself, one invertible matrix with itself, and then the conjecture is that the permanent rank of this matrix is equal to n. That means that it has a full pair rank. So this conjecture was proposed in his PhD, and actually he generalized it, I think, a year later with adjoining two invertible matrices A and B. This is instead of A and A itself. But A and A itself comes from another problem. This conjecture is being motivated by another conjecture by Allen, Judge, and Tarsi. In 1989, Allen and Tarsi proved the conjecture for some cases. In 1981, actually, Judge proposed this conjecture. It says that, let's say we have a field, it can be finite or infinite, but it has at least 4 elements in it. And also we have a non-singular matrix over this field. Then we can say that there are 2 vectors, x and ax, which is the multiplication of x with a, and they are both nowhere zero matrices. That means that none of their entries are equal to 0. Well, this conjecture, again, has been proposed in 1981, which is just half of decade older than me, and then it's been proved by Allen and Tarsi in 1989 for fields of non-prime powers. I mean, for the fields which have for the fields which are non-prime. So it means that the fields which are prime powers, but the power is at least 2. Well, let's take a closer look at this conjecture. It says that we have a matrix A, which is invertible. We want to find a vector x such that if we multiply this matrix A with that vector, we'll get yi's such that all the yi's and xi's are non-zero. That means that if you multiply all of them, also they are non-zero. But here yi's are nothing other than the matrix A times the row I of the matrix times x here. So we want this polynomial in xi's to be non-zero, not constantly 0. That is actually the idea that Allen and Tarsi used to prove the conjecture for non-prime fields. They looked at this. They looked at this polynomial in n variables, and then using Hilbert-Knowles-Stanislaus theorem, and reducing this polynomial to another polynomial over field of that characteristic p that they're assuming, they were able to show that this is not constantly 0. Unfortunately, the trick doesn't work for prime fields. So it is still open over prime fields. So yeah, Allen and Tarsi proved this in 1989. And also, I was working on this problem in my undergrad research. We were able to prove that every non-zero matrix just needs to have at least one non-zero entry. Is similar to an AJT matrix. By AJT matrix, we mean that it has a vector x such that if you multiply A with x, we will get a nowhere zero vector again. So we were able to prove this. It's been published last year. And also, we will see that the AJT conjecture is implied by the Perman conjecture. That's actually why it was the motivation for Young-Yu to propose that conjecture. So what it says, in the Perman conjecture, it says that, well, those xi's, if there are such xi's, those xi's need to be only 1 or 2. We don't need the whole field for those for that matrix X. The entries can come from the set 1 and 2. That's all the Perman conjecture is saying about the AJT conjecture. So here I want to introduce some new terms, and this is what I'm working on right now. It's about the term rank of a matrix. Term rank of a matrix is defined to be the maximum number of the non-zero entries of the matrix on a diagonal of the matrix. So we look at all the diagonals of the matrix. The maximum number of non-zero entries that we can find on a diagonal, that gives us the term rank of the matrix. Or equivalently, we can say that the minimum number of the rows and columns that cover all the non-zero entries of the matrix. For example, in this big matrix, well, it's big for me, maybe not for you. Well, we can look at this and we can say that these blue rows and columns, 2 rows and 2 columns, cover all the non-zero entries of the matrix. So that means that term rank of this matrix is equal to 4, and that's the minimum thing that we can come up. Or equivalently, we can say that these red ones are one of those maximum number of the ones that we can find on a diagonal of the matrix. So term rank of this matrix is, for example, 4. But what is it good for is that we want to propose this conjecture. We observe that for small matrices, small term rank matrices, permanent rank of A, which is the size of the greatest of matrix of A with non-zero permanent, is at least half of the ceiling of the half of the term rank of that matrix. Well, we observed this for per rank 1 and per rank 2 matrices, and that leads us to this question that if we can characterize all the matrices with their permanent ranks and relate them to their term ranks or not. So this is the conjecture. We hope that it is true, and the equality for this conjecture holds if and only if our matrix is similar. I'll define what this similar means, but it is similar to a direct sum of these kind of matrices, 1, 1, 1, negative 1. Well, for this 2 by 2, just this by 2 by 2 matrix, we have that direct sum. You will see that the term rank of this matrix is 2, and the permanent rank, if you look, the permanent of the matrix itself is 0, but well, the permanent rank is 1. So it is at least, that satisfies the inequality and also the equality here. So we say that, well, we can just put these on the diagonal of the matrix. That gives us a n by n or 2n by 2n matrix. And the term rank is going to be also 2n, but the permanent rank is going to be n. And those are all the matrices that we can we can find with equality here. By similar, we mean that we delete all the rows, 0 rows and 0 columns, first of all. So we don't want any 0 rows and columns. And then we reduce the matrix by multiplying non-zero entries, non-zero rows and non-zero columns by some entries by some numbers such that we reduce them to 1. So if I have, for example, 5 here, I just divide that first row by 5 and then multiply the second row by some number that fits so that I get 1. So and we also permute rows and columns in a correct order that we get these on the diagonal of the matrix. So this is the conjecture, and the questions that we are interested to look at is that, well, first of all, can we characterize all the matrices of the rank A? Well, we've done it to some extent, but we are still working on it. We don't know if we can do it for really large permanent ranks. The other question is that, can someone prove the AJT conjecture over just a field of 5 elements, order 5? Well, that's the first open case for the AJT conjecture, and well, in a long time nobody had any proof for that. And also, one thing which is not really too much related to my work, but I'm interested to know about is the computational aspect of this permanence of matrices. Can we compute the permanence of matrices in polynomial time or not? Well, one of the ways to attack this problem is that we want to convert computing the permanence of a matrix to computing the determinant of a matrix. But we want that the new matrix to be of polynomial size in n, because we want to at the end to be a polynomial order. Well, so far there is no polynomial algorithm known for computing the determinant of a matrix. Well, that was all. Thank you.
Time for questions?
The last question was, you want to know how fast you can compute the permanence.
Compute the permanence of a matrix in polynomial.
Is that because you want to know how fast you can compute the permanent rank?
Well, that's a general question. I said that it's not related to my work, but it's one of the problems that are out there.
I mean, the permanent rank is the size of the Matrix matching.
Yes.
So you might want to do this.
Yeah, that helps. But, well, that's of less hope to be able. I mean, it's also connected to P versus NP problem. So it's of less hope to be able to go through that way.
about other functions where instead of just plus and minus one, you put characters? Look at those things at all?
Well, people have looked at those things. They're called immanence of the matrices. And also there is a conjecture that relates permanence and immanence and determinants of the matrices in general together. I haven't worked on those, but yeah, I know that people are working on those topics still. Yeah, in general they are called immanence of the matrices, and yes. I-M-M-A-N-E-N. Okay.
Other questions? All right, well, we thank Ivan and all the speakers for the